Hello, I'm Sungful Moon from Naver Labs. In this video, I will introduce our paper, Co-op, Correspondence-based Novel Object Pose Estimation. Before introducing our method, let's look at two commonly used strategies for coarse pose estimation. On the left is template matching, which compares the query image with a large set of rendered images and selects the best matching pose. This approach generalizes well but requires exhaustive matching, which makes it slow. On the right is feature matching, where the model directly predicts 2D, 3D correspondences between the query and a single rendered template. This is much faster, but it usually depends on an accurate object mask in the input image. Our method combines the strengths of both strategies, aiming for accurate and efficient pose estimation without relying on masks or dense template sets. To overcome the limitations of template and feature matching, we propose a hybrid representation that combines patch-level classification and offset regression. On the left, patch-level classification allows the model to identify the best matching template patch for each query patch. This gives us a rough correspondence across images. On the right, offset regression refines each match by predicting a precise offset vector from the query patch center to the accurate match location. This hybrid design offers fast and accurate alignment, while remaining independent from object segmentation, effectively inheriting the strengths of both prior strategies. In our pose refinement stage, we build on GenFlow and introduce a new output, flow probability. As shown in the diagram, the model takes an input crop and a rendered image with the initial pose, and predicts dense flow along with certainty and sensitivity. Additionally, we model the flow vector probabilistically, using a Laplacian distribution with a learnable mean and scale. This allows the model to increase uncertainty in ambiguous regions and focus on reliable correspondences. On the right, you can see our flow loss, which penalizes both the flow prediction error and the uncertainty scale. This slide shows the coarse pose estimation pipeline, the first stage of co-op. At the top, you can see the overall architecture. Given an input detection, we crop a query and extract patch-level features using a transformer encoder-decoder. The model then predicts patch classification and 2D offsets to infer semi-dense correspondences. During inference, we retrieve the best matching template based on patch similarity, and use these correspondences to estimate a coarse 6D pose with PNP. At the bottom, we show qualitative examples. You can see the retrieved template, CNOS mask, matched patches, correspondences, and the final coarse pose. This slide illustrates the pose refinement stage, which takes an initial coarse pose and iteratively improves its accuracy. Given the coarse pose, we first perform pose condition cropping and render the object using the current estimate. These two inputs are processed by a shared transformer encoder. A decoder and a DPT module then estimates a dense 2D flow from the template to the query. To improve robustness, the model also predicts three types of confidence maps: flow probability, certainty, and sensitivity. These are used to weight the flow before passing it to a differentiable PNP module for pose optimization. At the bottom, we visualize the intermediate outputs and the final refined pose. Now let's take a look at some qualitative results. In the top row A, we show correspondences between the query image and the template from the coarse estimation stage. As you can see, our method successfully identifies meaningful matches, even in scenes with clutter and occlusion. The bottom rows B show the pose refinement stage. From left to right, we show the input image, initial pose rendering, estimated flow, flow probability, certainty, and sensitivity. Here's the quantitative comparison on the BOP challenge datasets. The table is divided into three sections. At the top, we show results using only coarse estimation. In the middle, we include pose refinement with a single hypothesis. And at the bottom, we evaluate refinement using 5 pose hypotheses. As you can see, our method, co-op, consistently outperforms prior works across all settings. Building on the quantitative results, we now present qualitative comparisons across multiple datasets and methods. At the top, you can see sample scenes from 4 BOP datasets: LMO, ICBin, HB, and TUDL. These examples highlight how our method performs under challenging conditions, such as occlusion and clutter. Below that, we show a detailed comparison on the YCBV dataset with GenFlow, GigaPose, FoundPose, and our method. For each method, we present both the coarse estimation and the refined pose. These results highlight the effectiveness of our approach in achieving robust pose estimation. Thanks for watching.